Welcome everyone to the Mid-Year Energy Summit webinar, and thanks for joining us. Today is part of a webinar series in conjunction with the Appalachian Mid-Year Energy Summit. This is the second webinar that we've had this spring. The next webinar is on March 18th, so please consider joining us at 2 p.m. where we'll talk about embodied carbon in the built environment with Jay Lanier from Interface Incorporated. Today, we have presenting Bill Pfleger, who is a Solutions Architect Manager in the Microgrid Competency Center for Schneider Electric. Bill is part of the Schneider Electric North American Microgrid Competency Center, where he currently serves as the team's project development engineer for North America. They're focused on microgrids, distributed energy resources, projects spanning from the customer side of the meter to the utility control meter. He also assists in general business development and marketing activities, as well as mentoring the Competency Center's solution architects, a team he previously managed. A few announcements today. All attendees are muted. We will have a Q&A at the end of the presentation, so please utilize the Q&A function on the bottom of the Zoom tab, and we will add those to the list of questions that we'll ask Bill at the end of the webinar. Also, this webinar is being recorded in order for us to rebroadcast it. So Bill, welcome to today's program.
Hey, thanks, Lee. So
yeah, Bill is no stranger to App State. He's an alumni, and it's really great to see you again.
Thanks, Lee. Yeah, it's great to be back. And if I could just go ahead and start sharing my screen, I think you might have to stop. There we go. All right. So again, thanks to the organizers for giving me this opportunity to speak here at the Appalachian Energy Summit. As Lee mentioned, my name's Bill Pfleger. Love to be back at App State. It's a place near and dear to my heart. And today we're going to be talking about microgrids and energy storage. We're going to talk about the new energy landscape. Then we're going to dive into a little bit about microgrids and their control systems. We'll transition topics to energy storage and how they can play a role in microgrids. And then I do want to leave you with some best practices when you're undertaking your own energy storage or microgrid projects. And then you'll hear from a couple of my customers, Schneider's customers at the end too, testifying about their experience in delivering microgrid projects and how it's serving them in their communities. So, a lot of people think that we're on the brink of disruption, and this disruption is really a shift in paradigm in how we as a society produce and use our energy. I would argue that we're already there. This disruption is already occurring and in fact desperately needed. And while I don't want to make light of what happened in Texas recently, it is pretty fortuitous timing for this discussion. I think that microgrids and energy storage really present a solution to what was ultimately a devastating and tragic situation in Texas. So with that in mind, what we see happening in our world is a great increase in electrical demand. You know, some people say this will double by the year 2040, and electrical vehicles are certainly going to be a part of that doubling. They can represent a tremendous increase in demand at your facility or at your home. And indeed one that your electrical infrastructure may not be ready to handle. And even if it is ready, maybe your utility company isn't ready to provide you the extra power. But even if they are ready to provide you that extra power, maybe you're going to have to wait a prohibitively long time period. In California, a service upgrade might take 2 years to get to you, for example. Or even if they can serve you with the power, you might not be ready for the impact that it's going to have on the financials of you operating your site and what that means to your electric bill. And so microgrid and energy storage present an opportunity, one opportunity in ways to integrate and manage that transition. So along with those things going on in the world, we're also becoming a much more digitized society. And so our buildings include more and more connected devices, and leveraging that information becomes an interesting topic. At the same time, people are investing in their own generation on site, and increasingly that's green energy. And even better still, that's green energy that's more cost effective than purchasing it from your utility. And so how are we going to leverage this data? How are we going to integrate these new generation assets to our site becomes an interesting question. So the disruption is here. And I think that really we're shifting from really a linear traditional model with centralized generation pushed through a utility transmission system and consumed by the end user to one that is multi-directional and complex, where you might be selling energy to the utility as well as buying it, and managing all of this is the emergence of the new paradigm in the new energy landscape. So along with those findings, a couple key trends are happening. So we're all very familiar probably by today with solar PV systems. Their costs continue to decrease as we get better at manufacturing and also as the efficiency of those systems increase. Energy storage systems are undergoing a very similar transition where their costs are falling rapidly, and we are better manufacturing those systems, so their costs continue to drop. There's also something called the spark spread. Basically, the spark spread is when you can purchase natural gas from a gas utility and use that gas on your site locally to generate electricity and also perhaps heat, and then use that locally cheaper than buying electricity from your electric utility. And so what all of these things add up to is that distributed energy resources, or those located at your site, are at parity or outperforming your electric utilities. And I only see these trends continuing as these technologies decrease in costs, and also as our utilities increase costs.
We're not seeing your screen.
Oh, really? Okay, let me see if I can stop and reshare. All right.
There we go.
You're seeing it now, but it's blank.
See a picture of the mountains.
All right. Oh, that's a beautiful area outside of Boone, North Carolina. So let me try sharing again. And Lee, I will make this slide presentation available so that if folks want to get it, we can get it to them. So if we missed any of the slides in the beginning, they will be available.
There we go.
All right, so hopefully now everybody's seeing these slides. Okay, so some of those key trends that I was mentioning before, the decreasing cost of technology and this new information, how are we going to meaningfully leverage these? What technology might be able to help us? Well, it should be no surprise to you, it's the subject of our talk today, microgrids. Microgrids with energy storage. So rather than show you a lot more slides and give you a definition of these things, I would like to play a short video that does a nice succinct job at explaining what a microgrid is and how it might benefit you at your facility.
Everybody knows what a power grid is, but what about a microgrid? A microgrid is a group of interconnected loads and generation sources, such as solar and battery storage, that are connected to, but can operate independently of, the main electrical grid. The beauty of a microgrid is that it can provide resilience when the grid is lost, but can also provide energy efficiency and financial benefits when connected to the main grid. With EcoStruxure microgrid technology, you can easily optimize the best times to consume, produce, store, and sell energy. It can also identify threats to the grid system from incoming storms or other disruptions and automatically leverage your facility's on-site distributed energy resources to keep you operational 24/7. And best of all, by maximizing your on-site energy resources, microgrids can reduce your carbon footprint and take advantage of state policies and federal incentives that promote clean energy. Microgrids can be a powerful addition to your energy system if you have or are considering adding distributed energy resources. If energy resilience is critical to your business, or if you operate in an area with high energy rates, or your region offers attractive financial incentives. Owning a microgrid or paying for a microgrid up front doesn't make sense for everybody. But we have good news. Together with strategic partners, Schneider Electric delivers energy as a service, an innovative business model that allows you to unlock the benefits of a microgrid without any upfront capital. Explore how you can fortify your energy future with proven microgrid solutions and flexible business models that empower you to transform your energy into a strategic business asset.
Okay, so hopefully we've level set a little bit on exactly what a microgrid is. The next few slides are really covered in that video, so I'm not going to go over them, but videos don't always print very well. So in case you're screenshotting now that you can see the slides, there's that information for you. And I do want to highlight a couple of key aspects. So the main drivers behind microgrid are really three things, in my opinion: cost, resilience, and sustainability. And I want to talk about one point related to costs. While it's true microgrids can lower your operating costs or your energy costs, what's often equally as important to organizations that are working within a budget is having very predictable costs. And that is something else a microgrid can deliver on, perhaps to a greater degree than your electric utility. And Texas is a great example of that, when you've seen some of the headlines coming out with people having thousands of dollars of bills for 1 month when typically they were paying maybe just a couple $100. So one point about cost I wanted to point out. This definition is almost given verbatim in the video, so I'm not going to go over it, but I did want to talk to you about the term distributed energy resource. Realistically, there are three categories of distributed energy resources, or a DER. You may hear me refer to it as a DER or DERS during this presentation. The first category almost everybody gets, and that is a generation source, something that produces an electron. So that could be a traditional diesel backup generator, or maybe more idealistically today, a renewable energy source like solar PV or wind. The second one is also fairly well understood, and that's energy storage systems. And there are many of those, and we'll talk more about that later on in the presentation. But the third one is often overlooked or forgotten, and it can be equally as important to a microgrid, and those are flexible loads, things that you can turn on or off or up or down. And so one example might be your building's HVAC system, where you can turn the temperature up or down or turn the system completely off. The video talks about two of these types of microgrids already, but it leaves out a third that I did want to point out, which is off-grid microgrids. These are particularly useful for remote communities or in areas where the utility can't provide power yet. Microgrids also come in all shapes and sizes, from residential applications all the way up to campus-style microgrids like Appalachian State might consider implementing, or even a subsection of a wide area utility network. I did want to spend a little bit more time talking about what microgrid projects consist of. And the first one here is often overlooked by customers when they're planning their microgrid budgets and projects, and that's engineering and ongoing operation and maintenance and services. A lot of people have the understanding that when they buy microgrid equipment, it comes with engineering, and to a degree, that's true. But there is also additional engineering that has to be undertaken as part of these projects, anytime you interconnect a new generation or storage asset to the utility, engineering is just simply required. And anytime you alter an electrical network at your local site, engineering stamped and certified documents are going to be required as well. So don't forget that. These systems also involve a lot of different types of equipment. So there's electrical distribution equipment like switchgear, switchboards, circuit breakers, these kinds of things. And they also involve distributed energy resources. Now, we've talked a little bit about them already, but there is one distributed energy resource that is more important to a microgrid than any other, and that is your anchor resource. When your microgrid is grid connected, your anchor resource is the utility itself. And what it's doing is providing a stable voltage and frequency reference. Now, I don't need to get into electrical engineering with you, but what's important about this is that when the utility goes away, so does that voltage and frequency reference. And so something within the microgrid itself needs to substitute for that utility voltage and frequency reference. And we call that asset an anchor resource. Traditionally, these are rotating machines like a generator or a gas turbine, but increasingly today, they can be an energy storage system when paired with the correct power electronics. And we'll talk a little bit more about that later in the presentation. And then the other major aspect of microgrid projects are the software associated with them, of which there can be many different flavors, and we'll discuss a couple of those too. So a little bit more about what the major components of microgrids are. One important aspect of microgrids are loads and what types of loads are present at your site. And beyond that, being able to prioritize those loads in terms of their importance to your operations. We've talked a little bit about electrical distribution equipment that's involved in these projects already. One thing I did not mention yet are the grounding and protection equipment that are often associated with microgrids that are very important because you're now kind of operating a mini power plant there at your facility. Distributed energy resources we've touched a lot about, so I'm going to skip over to the next two columns, which are actually really just microgrid controls in general. And I want to dive a little bit deeper into microgrid controls next. And the first thing I want you to know about microgrid controls is that there are three levels of them: primary, secondary, and tertiary controls. Primary controls are those that are baked into the subcomponents of the microgrid themselves. And they act very, very quickly, and they take action all by themselves. And they're really doing this because of safety reasons. They can also collect data. As you recall, more and more devices are becoming connected in our building, and so they're producing data that we can leverage within the microgrid. But let me give you a couple examples of this. So everyone should be fairly familiar with the circuit breaker panel box you have in your home, and a circuit breaker itself has primary control in it. Basically, if too much power goes through that circuit breaker, it trips open and prevents electrical fires. No one has to tell it to do that. It just automatically takes action, and it takes that action very, very quickly to prevent a problem from occurring. The same thing is true for, say, a solar PV inverter. If the inverter sees that the utility has disappeared, the inverter will rapidly shut itself off. And again, it does this out of concern for safety, because the PV system doesn't want to produce electricity and send it onto an electrical grid where some lineman from the utility company may be trying to make a repair. All right, so these things act very, very quickly. They're very concerned with safety. Now, the next layer up, our secondary level of control, is where things start to get interesting. And that's our power management systems. This is the proverbial microgrid controller. It will also act really, really quickly because it's concerned with resiliency and balancing power and load. And we'll talk a little bit more about that in just a moment too. And then think where the real magic of microgrids happens is actually the tertiary level of control. And this is your energy management platform. And it's looking at things in longer time duration, minutes, maybe hours. And it's looking at how to use your microgrid to best your ROI, or your return on investment for that asset. So I want to focus in a little bit on the secondary and tertiary levels of control, but all three are represented in this conceptual microgrid architecture. So at the very bottom, we have our primary devices. We're going to ignore those for now, but they are feeding data up to our secondary level of control, our microgrid power management system. And the power management system is really concerned with two primary tasks. First, it's looking to see if the utility grid is present or not. If the utility grid disappears, it steps into action and physically isolates the site from the utility grid. Once that isolation has occurred, it will then bring up on-site generation assets and match the load and the generation together. Finally, when it sees the utility signal return, it will reconnect the microgrid once it has synchronized the microgrid to the utility grid. And so it does this in a very safe manner. I should also mention that the power management platforms are often paired with a local workstation, some interface where an operator can query or manually control the system if desired. But what's more exciting to me is the tertiary level of control, because this is the state of your microgrid being optimized while it's grid connected. And most of the time, our microgrids are going to be connected to the utility grid. And so it's doing a lot of stuff. First, it's understanding what's happening on your site in near real time, and it's receiving that information from the power management system. But not only does it understand what's happening in near real time, it's also cataloging what has happened historically. And it's learning about how your site uses energy over time in order to make better predictions on how to manage your energy in the future. So there is actual artificial intelligence and machine learning going on in this platform. But beyond understanding what's happening at the site, both at a near real time and historical level, it's pulling in other information from the cloud. And one example of that are operational constraints. As I mentioned before, your HVAC is a potential flexible load that can be optimized. But when we're in our buildings, we like to be comfortable. And so we might say, hey, energy management system, you can use the HVAC system, but you can only operate it between the bands of 65 degrees and 75 degrees. And so that's just one example of a constraint that might be considered by the platform. There are many others. Maybe more important to that is it understands weather forecasting information. So it's going to understand how much the sun is going to shine, how much the wind is going to blow, and then it's going to use that information to understand, hey, what's the HVAC load on my building likely to be like today? How much energy can I produce from my solar and wind systems? Will I have excess energy to store in my battery system? Or is there severe weather coming my way where I might want to be ready for a potential islanding event and ignore economics for the next couple hours? So it's internalizing this information. Perhaps even more important than that is it's understanding how you're buying your energy today. So does my electric tariff have seasonal price variation? Does it have time of use price variation where I might be paying different amounts of my energy at different time periods during the day? Do I have what is called a demand charge, where if I exceed a certain amount of power draw from the utility, I have to pay extra for it, or get penalized and pay even more? And maybe this ratchets. The more I increase my demand, the more I have to pay. And so it will understand how you're having to purchase your energy. And finally, these systems understand what is called ancillary services, which is really, if it's available in your area, it's an incentive program offered by the utility to take certain actions at certain times of the day and generate revenue as a result. And one example is a demand response, whereby the utility might say, hey, if you reduce your load, we will pay you X dollars per kilowatt. And so it takes all of this information, It crunches it through some fairly sophisticated algorithms, and the end result is it produces a forecast of when it is most optimal for you to produce, store, buy, or sell energy locally at your site in order to gain the best economic return for the investment of those microgrid assets. And together, these two components, the energy management system and the power management system, are called the Advanced Microgrid Controller. Now, I should mention one other thing. The system that I've just described to you today is the pinnacle of capabilities currently available in the market. So you may encounter systems that have the ability to do subsets of what I've discussed, but this is kind of the art of the possible today. Now, with that being said, I want to transition topics to energy storage. Energy storage can be an incredibly powerful and important aspect of microgrids, but there are many, many different types, and not all of them are created equal. So there's thermal storage, flywheels, pumped hydro, compressed air. But these tend to be expensive and take up a lot of land. So probably what we're more interested in talking about are batteries, deep cycle lead acid batteries, glass mat batteries, even flow batteries. But kind of the king of the hill right now are lithium ion batteries. But just like energy storage systems, there are many different chemistries of lithium ion batteries, and they all mean a little bit different thing. And I want to focus on kind of two of the most common ones and the up and coming chemistries. Just know that there are other chemistries of lithium ion batteries beyond these three out there in the market today. So currently the king of the hill is NMC. It's the most common applications are EVs and stationary storage. Right now they have the best energy density and the best pricing, but they're typically not well suited for indoor applications, and they can have thermal runaway issues and fire issues if not properly managed. I think probably a lot of you have heard of or seen videos of Tesla cars catching on fire. These are using NMC batteries. And if we're not properly managing, the same thing can happen for our microgrid batteries. LFP chemistries are kind of the next great thing. And in fact, that transition is already occurring. Previously, they were not very cost effective. They were much more expensive than NMC, but those costs have come down dramatically. And they are less prone to thermal runaway. So they make for a more safe chemistry to implement, but they are more susceptible to thermal degradation. And we'll talk a little bit more about that in a moment compared to NMC. And if you're forward thinking, kind of the next chemistry that's interesting are LTO batteries. Right now, they're not cost effective, but their costs are coming down. And they make all the promises of the positive aspects of our other two chemistries. In fact, they promise to take it even a step further. And so I see this as the chemistry that will be coming on board next, maybe in the next 5 years or so. Beyond that, and I didn't include it in the slide, there are also what are called solid state batteries. And if I look 10 years out, I see solid state batteries becoming more of a player. But today, they're a little bit too much of a science experiment, and we'll probably see the first applications in electric vehicles before we see it in stationary storage for microgrid applications. So a little bit more about batteries. Battery is really just one component of an entire system, right? So a battery energy storage system, or a BESS, is what you're seeing in the upper right here. And there are many components. There are two main components. We've talked about one of them already, and that's the batteries themselves. The other main component is the power conversion system. This is incredibly important. If you want to use that resource as the anchor resource for your microgrid, you need to make sure it's coming with the right PCS. It needs to be bidirectional and a grid forming true 4-quadrant inverter. Those are some buzzwords to look out for when you're reading about batteries. If they have those applications, that battery can be used as an anchor resource. They also contain battery management systems. As mentioned before, that's a very important aspect. And you can see an example of a network diagram here in the lower right of a battery network for the battery management system. Very important for safety reasons to avoid thermal runaway and these types of things. And a good battery is going to get you around 89, 90% round trip efficiency today. Now, one of the most common questions I get asked are, how long is my battery going to last? And realistically, it depends on your use. 10 to 15 years or around 5,000 full depth of discharge cycles is common. And by depth of discharge, I mean taking it from around 99% state of charge down to around 4% state of charge and then back up to 99%. But this will vary by manufacturer. And they typically come with around a 3-year warranty as standard, but you can often purchase options for a 10-year warranty. Currently, a 10 year is about the longest you're going to see out in the market. And that's typically because the power electronics or the power conversion system has a mean time rate of failure around 10 years as well. And so these things kind of coincide with one another. Does that really mean your inverter is going to fail after 10 years? Probably not, but you're taking a risk after that point. Now, I expect those durations to be extended as battery degradation gets better and also as inverters are pushed to match that battery degradation better, similar to what we've seen happen in the PV industry with the inverter warranties and lifespans that are more matching module lifespans in PV industry. But I say the important thing is the life expectancy depends on your use. And a lot of people want to use the number of cycles as an indication of how you're using the battery. And I would argue that that is not the best way. It's really about thermal management of your battery. So if you have 2 identical batteries and you take one and you discharge it at full power and then you charge it right back up at full power, and then you do that again and again, and you take a second battery and you discharge it at full power and then you let it rest for 2 hours, and then you charge it back up at full power, and then you let it rest for 2 hours, those batteries are going to degrade very differently. And in fact, the second battery there is going to last a lot longer and experience a lot less degradation. Just like with your cell phones, when you feel them getting hot from being used or from being charged, if you don't let them rest, your battery in your cell phone is actually going to die a lot quicker, right? And the same thing is true for your larger energy storage systems. So I mentioned that batteries can be incredibly powerful for microgrids, and that's really due to their flexibility. They can be that anchor resource. They're also very, very fast reacting, okay? We don't have to wait for a generator to spin up. These things can react sometimes in 40 milliseconds or less. So they can be very quick, and they can help with power quality issues if that's an issue you're having at your site. And they can also help with intermittent renewable production. So if a cloud rolls over your PV system, that battery can step in almost instantaneously to fill in the gap. Which the end result means that potentially with the right size battery, you can green your energy mix 24/7 around, full calendar year. However, they are likely to be the most expensive asset in your entire microgrid, even though costs are falling. And there are incentives like the federal investment tax credit that can help reduce the cost of these assets. But I should mention that if you want the full 26% discount from the ITC, you need to charge that battery from 100% renewable energy. There is what they call a waterfall effect at 75%, where you will get below charging 75% of the time with renewable energy, you will get 0% of the tax credit. And it's linear between the two. So if you charge the battery, halfway between 100 and 75%, you're only going to qualify for 13% of those tax incentives. So I might recommend undertaking a study to minimize the size and therefore your investment in a battery energy storage system. One other potential drawback is that they have a limited tolerance for inrush. Many of you may not be familiar with inrush currents, but there are certain types of loads, going back to why it's very important to categorize the loads you have at your facility. There are certain loads out there, like a motor load, that has a very quick spike of power draw. And so maybe a load is typically 100 amps, but during this momentary inrush, it might be 600 or 1200 amps. And if your battery system power isn't rated to handle that, you could experience problems. And typically, the inverters tied to batteries are rated for around 110% over power for a limited amount of time, like typically around 10 seconds or less. So if you have a 100 kilowatt power rated battery, it might be able to provide 110 kilowatts momentarily to help manage inrush. But if your inrush is greater than that, you're going to have a problem. Now, I also want to talk about the two main designs for battery energy systems, and that is AC coupled systems and DC coupled systems. I don't want to get too deep into the weeds on the specifics of those, but I do want to mention that, in my opinion, AC coupled systems are better for microgrid applications, whereas DC coupled systems are better for utility connected PV and storage systems, as well as proving the renewable energy was used to charge the battery in case you get audited by the IRS when you're claiming your ITC. And the reason I say that AC coupled systems are better for microgrid applications is really two main reasons. One is the DC coupled system has a single point of failure with one inverter here. And the other is that since you have, let's just imagine this is 100 kilowatts of battery and a 100 kilowatt PV array behind a 100 kilowatt inverter. In the same scenario with the AC coupled system, if we had a 100 kilowatt battery, 100 kilowatt PV array, we have an additive effect where we have 200 kilowatts of potential power to support loads. So we can support more in an AC coupled system. Another couple important considerations. If you've heard the term UPS, or uninterruptible power supply, you know that it's pretty much a battery. But don't be confused, because they are very different from a BESS, or a battery energy storage system. And I only say this in case you buy one expecting to get the functionality of the other. You're going to be disappointed. They don't act the same. They don't work the same. So just be aware that those are different products out there in the market. If you have questions about it, I'm happy to explain more on that later. I mentioned this before, but consider paying for a study to right size your battery. Some companies might do that for free for you, by the way, too. And realistically, there are two reasons you size your battery. One's for resilience and one's for economics, and they're often opposing forces. And so paying for a study can help you find a happy medium, or find the right battery for you, so that you're not buying too much battery, which might represent a significant cost increase. Also consider where that battery is going to go. Do you want it to go indoors or outdoors? That might have implications for the chemistry that you select. There may also be implications related to that for fire and building codes. For instance, you're not going to be able to put a lithium-ion battery indoors in New York City. You've got a better chance of becoming our next president. And then also, those codes may have implications for the certifications that must be achieved by those energy storage systems. So make sure that those certifications are in line with the products that you're looking at, or put that onus on the respondent to, say, an RFP. I would also suggest working with a trusted and established vendor, somebody you know that's going to be around for the duration of the lifespan of your battery system. Batteries are being quickly commoditized, just like in the PV industry. Learn from the mistakes of the PV industry, where they went with the absolute lowest cost inverters just to have a lot of those companies go belly up 5 years later into a 10-year product. Don't get stuck with a product that has nobody around to support it again. And a lot of this is tied to achieving fire certifications. There's some significant costs wrapped up in that are causing a lot of companies to just give up or be absorbed by other companies. And then the last thing I would point out is think about the contractual terms for acquiring batteries. This is particularly something I see in the federal space, as well as with the Department of Defense. They like to put things in 25-year-long contracts, and realistically, it just doesn't make financial or logical sense. It's much better to shoot for the lifespan of the battery, maybe 10 or 15 years, and then replace it with something that's far more technologically advanced and likely to be a lot less costly. So keep that in mind too. All right, with that said, I want to transition topics again and go look at best practices and lessons learned from microgrids, and then let you hear from a couple microgrid customers. So just like batteries, I highly recommend working with vendors and contractors with a proven track record. Better yet, those who can take you to a project that they've done and show you how it operates so that you can have some assurance that you're going to get what's promised to be delivered. Don't become somebody's science experiment, somebody's classroom. Use somebody who knows what they're doing. The other thing I would suggest is if you're looking at implementing a microgrid project, see if you can assign a monetary value to resilience and then get the proper buy-in throughout your organization. I'll give you a quick example of why that's important. I was working with a manufacturing company up in New England, and the microgrid just wasn't penciling out for them in the time frame that they needed it to pay for itself. And we asked them, well, do you experience outages? And they said, yes, yeah, we actually do. We have about 5 a year. And we said, well, hey, what happens during those outages? Do you have to send your factory workers home, and do you have to still pay them? And they said, oh, yes, of course we have to pay them. And yes, we absolutely have to send them home. It's a safety issue. And we said, well, could we not consider the wages that you've paid as a revenue savings for introducing to the microgrid cash flow? And they got the proper buy-in, up to their C-suite saying, yeah, that makes total logical sense to us. And wouldn't you know it, that extra couple $100,000 of avoided costs with no productivity was enough to make the microgrid exceed their hurdle for payback by several years. So that was a great example of how to place monetary value on resilience. And it's not always possible for people, but if you can, try to figure that out and get buy-in. Mentioned this before with batteries, but consider a feasibility study, okay? And to me, it makes a lot of sense to de-risk a very large investment by paying a small amount up front to figure out if that investment is right for you first. And indeed, some people out there may also do it for free. A lot of companies like Schneider Electric, they may not do it for free, but we will credit your project with the cost of that feasibility study if you decide to move forward with the project with Schneider. And a lot of other folks will do the same. So it's almost a zero risk type of an investment with a huge de-risking upside. As I mentioned early in the presentation, don't forget about the engineering design studies and their costs. But beyond that, microgrids share more than just electrons. They also communicate. Remember all those new connected devices inside of our buildings? Well, they share data. And so beyond electrical wires running everywhere, don't forget that you also need to have communication wires running everywhere. It's a cost that's often overlooked. And depending on how far you have to run those wires, it could be a significant cost. When you're going to engage others about your microgrid project, I use the phrase garbage in, garbage out. So the better the information you can provide them, the better and more realistic designs and expectations and costs they can put around the project that you want to implement. So this type of information might be useful, say 1 year's plus worth of electric bills, 1 year's or more worth of electrical interval data, which is basically just data that shows how and when you're using your energy on your facility and at what rate. Keep in mind, 2020 was a weird year. So if COVID impacted your energy use at your facility where you implement a microgrid, maybe go for a different year with that interval data so that we have a more accurate understanding of how you use energy at the site. Site location is critical. Also, if you can produce layout drawings or some indication of where equipment can be placed around the site, that's very helpful. Also, any information you can have about your existing electrical equipment or any distributed energy resource equipment. And then remember the loads that we keep talking about inside of buildings. If you have an idea of what your loads are and you can classify what they are and or assign a prioritization of their importance, this can be helpful in informing how a microgrid operates. Now, we haven't talked about actual costs of microgrids too much, but you've heard me mention costs a number of times. And a lot of people find that doing a microgrid in one shot is just cost prohibitive, and they need to do it over time in a phased approach. And I strongly encourage you working with a microgrid development group or entity that can help you create an energy master plan. This is the most critical aspect of doing a microgrid in a phased approach. I can't tell you the number of times where I've interacted with folks and they've made great investments in some really fantastic assets. You know, one year they went out and got a PV array. The next year they went out and they got a CHP plant. And then the next year they invested in a battery. And now they're coming to us looking for a microgrid control system to make it all work together in concert and really deliver a much better value. And we have to ask them the hard questions like, hey, when you procured your PV system, did you ensure it has the right inverters that are going to be controllable by a microgrid control system? And a lot of the time the answer is, I don't know. Or we say, hey, you know what? CHP systems or combined heat and power plants, they're notorious for having control systems that are closed and they are not open source. So an outside control system can't coordinate with them. Did you source an open source control system for your CHP system? Well, I don't know. Okay. Well, what about communications? When you put that plant in 250 feet away from your building and your PV array in the field behind it, did you run communication wires along with your electrical wires back to your building? Oh, no, we didn't. And so if you have, you know, a master plan in place, you can avoid for having to pay for things twice, or you can avoid having to replace equipment that you just purchased, or augment that equipment. You can do it all in one shot. Particularly too, if there are planned projects that you're going to be doing related to your electrical infrastructure around your site, you can rope those into the energy master plan and find additional ways of reducing the cost, the upfront costs of microgrids. So be extremely open and upfront about all aspects related to a microgrid project. It'll help you find cost efficiencies and it'll also help you avoid scope creep that might be preventative for your project moving forward. Along with that, you're going to want to survey your existing equipment, make sure that it's in good health. If you're really trying to implement a microgrid for resilience, it doesn't often make a lot of sense to use outdated, dilapidated, poorly maintained equipment as we often see in our buildings. So keep that in mind. When you're planning the project scheduling, be aware that right now, because of COVID and just sheer demand, industry lead times are at an all-time high. And so try to judge that as you're putting your scheduling of your project together so that it can be implemented in a realistic time frame. And one other point on this is utility interconnect agreements. Anytime you put a generation or storage asset on your site, you have to set up an agreement with your utility on how that is allowed to interconnect with and interact with their grid. And I don't care how long they tell you that agreement is going to take to put in place. It's going to take longer. So I say triple whatever they say. So if they say 30 days, plan on 90. If they say 90 days, plan on it taking triple. A lot of people also think, hey, you know, I'm going to save some money by going a manual control route instead of an automated, autonomous control route. And for the right person, the right organization, that might make sense. But ask yourself the hard questions. Do you have a qualified person on site that can operate that system for you? Are you willing to pay for somebody to be trained to do that and then available 24/7 to do that? Or are you willing, or are you going to need to employ a new person to do that? So oftentimes manual cost savings don't actually equate to cost savings, particularly over the lifespan of that equipment. And then the last thing is somewhat of a shameless plug for Schneider Electric, because I do believe this is something that we do better than anybody else and almost exclusively in the industry, which is consider an integrated product to make your life a lot easier. When I first started working in microgrids, I would hear from customers all the time, why is this so hard? Why do I have to take so many shutdowns and have so many interruptions at my site? Why are there a million different contractors running around my site? Why is this just so complex? Why can't you guys just drop off the microgrid like you do when I order switchgear or normal electrical equipment from you? And we said, you know what, Mr. Customer, you're right. And so we created this integrated product you see on the right of the screen here called the Energy Control Center, which is a modular, scalable approach to microgrids. So as your energy needs change, this project can evolve, or this product can evolve with you. It's factory assembled and tested, so you know it works when it shows up at the site. It really cuts down on the commissioning and testing in the field of these systems. It also looks like a piece of traditional electrical equipment. So electrical subcontractors that have to perform the work on your site know what they're doing with it. It's very familiar to them. And so that reduces installation times, it reduces in the field installation errors. And it really truly is a microgrid in a box that can be dropped off just like those customers were telling us we needed to have happen. And so you can see here, it has integrated controls. This is a touch panel interface where folks can come with the proper login credentials and query or control the system if desired. And then it has the built-in automated communicated data sharing breakers for your loads and your generation sources. And so it is truly a microgrid in a box. And what I want you to do next is let you hear from a customer who implemented a microgrid using the Energy Control Center.
Fossil fuels are not an endless resource. We need to start working today to manage those energy challenges of the future. Renewable energy is real. On-site production of energy is real. It's resilient, it's sustainable, and it's cost-effective. My name is Charlie Fredrickson. I'm Vice President of Investments with Faith Technologies. We knew we wanted to build a microgrid to demonstrate how we can create our own on-site renewable energy. We chose the Fox Cities Environmental Learning Campus at Bubolz Nature Preserve. Their focus is educating the community about nature. Faith and Schneider work so well together. We could tell that they saw the vision of what we wanted to do, and they went all in with creating solutions. Our microgrid is very unique. We have 5 different distributed energy resources: a solar PV field, natural gas generator, microturbine, battery, hydrogen fuel cell, and the electrolyzer. With the Schneider Electric Energy Control Center and EcoStruxure Microgrid Advisor, we're able to take all 5 resources and manage the power in one unit. So it's collecting data as it relates to weather patterns, the cost of energy out on the grid, and how it's going to use that data to optimize the operation of the microgrid. Faith and Schneider received the very first Distributed Energy Resource Project of the Year award. The construction of this microgrid is really a tribute to the strong partnership between Faith and Schneider. On-site power generation is the future.
All right, so hopefully at least some of you are interested in microgrids and projects, but maybe a lot of you are concerned about the costs. There's good news. Microgrids can be implemented with no money down in what is called an energy as a service project. And it's more than just financing. It's about letting the customer of the microgrid specialize in what they're good at, and then taking the risks of the microgrid project and pushing that to the energy as a service provider. It operates very similarly as a solar PPA, basically frees up the customer capital. It protects them from financial, regulatory, technical risks, because again, the energy as a service provider owns that. You're going to have your system operated and maintained by people who are actually expert in doing this. You're going to have predictable long-term costs for your operating budgets. And you're, at the end of the day, you're going to get a more reliable and green microgrid system compared to your utility. And so next, I want to share an example of a customer who did exactly this. In fact, they were one of the first customers in the world to implement a microgrid solution as an energy as a service project.
Montgomery County, located in Maryland, is a community that's just on the outside of Washington, D.C. We're over 1 million people, and we have from urban to very rural type environments. My name is Michael Yombrock, and I am the Capital Energy Project Manager. Because we've seen a lot of weather-induced incidences recently that put about 250,000 people without power, we started looking at developing microgrid systems. From the county executive on down, we are very intent on keeping pertinent and important functions that service the community up and operating in the event of a power grid outage. Working with Schneider Electric, we identified 2 of our major facilities, public safety headquarters, and the other is our correctional facility. If a grid goes down, using the EcoStruxure system, we're able to provide electrical power from the facility by both the standby generators, the CHP, and the solar. We financed the project using energy as a service. The county pays no money up front. Duke Renewable Energy came in and financed the project, and Schneider Electric assisted us with the development, all the way from conceptual design to commissioning and validating the operations of the system. Their EcoStruxure system is one of the prime reasons we selected Schneider. It's state-of-the-art technologies, being able to bring these disparate generation technologies together and operating in sync. Montgomery County will continue to grow. We want to make sure that the community is safe and secure. We're very excited about being one of the first in the country to do a microgrid and be able to provide continual services to the communities.
Okay, so thank you very much for your time. I hope you guys found that interesting, and I will entertain questions now.
Thanks, Bill. That was perfect.
Yeah, sorry we missed a couple slides in the beginning there, but hopefully the message still came through.
No, it did, loud and clear, both on the fact that this is doable. This isn't, technology that's out of reach. This is technology that's happening all over the place. And then, just all the creative ways that you've really shared with us to be able to, make the business case for it, I think really resonate with me. And then, and really the need to take a truly integrative design approach. I know that we harped on this back in the days in building science, right? But it translates to all kinds of project development. So that really rang through. I was looking on Amazon for this in a box. I couldn't find it yet. It wasn't available. No, but the integrated approach, is fascinating, and you all clearly have a lot of experience. We do have a lot of questions, so I'm going to jump into the questions. One related to the box: does the microgrid in a box come with its own power conversion system, bidirectional inverters, and is it a DC coupled system?
Very interesting question. So the product that I showed you, the Energy Control Center, does not include assets that are for the individual DERs. It only includes means of controlling those. So the inverters and whether that system would be DC or AC coupled would happen outside of the box. But the information flowing from those systems, as well as the power, goes into the box, is managed, and then goes out of the box to your loads on your site. Now, with that being said, Schneider this year introduced at CES a residential version of this product, and that product does have the capability to include a solar inverter inside of the box. So at the smaller scale, we are doing things more in line with the spirit of that question, but at the larger scale, these systems are of such a size that that box would grow to be an impractical device and something that couldn't be standardized in our manufacturing process, particularly when we start involving third-party content and when these things have to go through what's called UL certification. So there are electrical code certifications that have to be achieved, and those are achieved through approving standard design approaches. And when we start pulling in a bunch of random parts, it becomes almost impossible to achieve that. But that doesn't mean it's not compatible with all of the aspects that that question asked.
Great. So another question, what kind of demand side management or commissioning are you doing with new clients to reduce the amount of generation and storage needed? Also, are you interfacing with third-party BESS systems?
So I'll tackle the first or the second part of that question first. And absolutely, in fact, one of the very first microgrid projects I worked on, we integrated with one of our main competitors, building automation systems, which is a Siemens system. But Schneider also offers building management systems. We interact with them all the time. And typically, we let this building management system specialize in what it's been programmed to do, and we issue it recommendations, and then it will decide whether those recommendations violate an operating constraint that has been programmed for that end user or not. And so it will deal with the flexibility that's available within that defined BAS system. What was the first part of that question again, Lee?
What kind of demand side management or commissioning are you doing? Yeah.
Yeah, so a different division of Schneider, our energy sustainability services, will help with reducing your electrical energy demands and requirements. So we often work together to deliver projects, frequently to MUSH markets and the federal and DoD, Department of Defense space. But me personally, I don't get involved with that because my business unit is specifically for microgrids. However, we as Schneider, as one entity, will tackle those things together, or we'll work with a third-party provider of your choice. So if there is a firm or an outfit out there that's doing energy audits and energy efficiency retrofits to do what I like to call megawatts, this is a fantastic idea to achieve first, because you can often accomplish energy efficiency much more cost effectively than implementing these big, robust electrical equipment and systems. And what you're doing is reducing the need and the size of those systems so that when you go implement them, they're a lot less expensive. And so a project from a total global perspective, an integrated approach like this question suggests, is an excellent idea.
So another question about commissioning, just curious about strategies related to kind of post install advanced commissioning, how long that lasts. Is that something that gets handed over to a team or individual that interacts with a microsystem controller?
Yeah, so a basic timeline: equipment is designed, equipment's manufactured, equipment's installed on site, and then a team of Schneider experts comes out and commissions it. And basically, when we're commissioning the system, there is a specialized group within Schneider that does that activity. It needs to be coordinated with vendors that are providing other pieces of equipment that's part of that microgrid system often. For example, if you're buying a battery, say from Tesla, like we saw on the screen in the slide, the Tesla engineers might want to be present when we're commissioning the microgrid system, because you may have to tune their inverter to work better. There's a lot of eccentricities to these things. So there is a team that will go out and do that. That team, if desired, will also train people on site in how to operate the system so that when we leave, you're not just left wondering, how do I work my system? And of course, training manuals, installation manuals, all that stuff gets turned over to the customer as well. And then, as far as how long does this take, it's highly variable depending on the complexity of the system that we're implementing. So usually I would never suggest it's going to take less than 5 days. We will perform this on off hours or weekends if that's preferred for the facility, like if you don't want to take any interruptions. But a minimum of 5 days. And then for very complex, for example, we just finished commissioning a system for the Department of Defense at MCAS Miramar out in California. That took months to commission, not just because Schneider had to do its work, but the government has a special commissioning procedure on top of that and a validation period. So they can take a very big different range of times to commission depending on exactly what is baked into your system.
Gotcha. So for flexible loads, could you expand more on how Schneider balances occupant comfort with shedding HVAC loads?
Sure. So there's a couple ways that we can manage that, and I'm going to limit my answer within the microgrid system itself, okay? Because there's additional things that can happen within the building management system itself. But basically, if we know the constraint of the site, then we will manage within the constraints. So as I mentioned, there might be a temperature range that we're allowed to make suggestions and play within. We may have occupancy sensors in the building, so we know when people are present in different areas, and maybe we're able to shut things off at that point in time. But realistically, we're going to issue those recommendations to the BESS system to execute. The flexibility, boy, it can range, and it just depends on what you're really trying to achieve. And also the relative cost of that. One of the things that the system does pretty well is understand. I'm happy to give demonstrations to people in the future on when we've done this. But one of the things that we like to look at is thermal inertia swing in the building. And so, as I mentioned, there's some machine learning, some artificial intelligence that's understanding the operation of your building better and better the longer it is able to be connected to it and learn. And so if we know that we want to be able to shut a building off during, say, a high cost of energy pricing period, we might actually ramp up and precondition the building to the absolute highest amount of threshold so that we can turn it off during that high pricing period completely. And then the thermal inertia will have us ride through that band of occupant comfort. And then once that reaches the lower limit, the system will power back on. But in doing so, we've avoided as much as possible paying for that more expensive energy. And I actually have some graphs that show that. I didn't include them in this presentation, but I'm happy to have a follow-up and go through that with folks.
So I missed a follow-up related to the bidirectional inverters. Are there particular bidirectional inverters recommended for your in the box system?
Actually, no. I'm happy to say that as long as the inverter is not proprietary communication protocols, these things tend to speak in Modbus or IEC 61850. For those of you who are more technically minded, you probably, or CAN bus, you probably know this. I'm happy to say that as long as the systems have been open, there's not been a single distributed energy resource to date that we have not been able to interface with. And many, by the way, are already preloaded into our platform. And this is not necessarily unique to Schneider. Others will do this too. But that preloaded functional block defines how our controller is going to have to interact with that inverter. And that can actually expedite and lower the cost of the project. We've integrated many different suppliers. Just a couple off the top of my head here, Tesla, Dynapower, our own battery. we manufacture our own battery. So that to date, there hasn't been anything we haven't been able to work with.
Great. Same person is wondering, potential customer question, are Schneider's teams scalable to handle new municipal, county, and or school system customers who are preparing / planning to seek installation in the next 18 months in North Carolina?
Sure, we'd love to have those conversations with you. Absolutely. You've got my number on the screen, my email. Feel free to drop me a line. I'm happy to connect you with the right people, and I'll probably be helping you personally.
So the last few questions here have to do with supply chain. There have been several about end of life for batteries, and curious about recycling and how to handle with potential hazardous substances.
So this is a really hot topic in the battery world, and I'll just be honest and upfront with everybody. The industry really hasn't figured it out yet, and Schneider's not an exception to that. We are continually trying to find ways to make these systems more sustainable, and recycling them is one concern, or what do we do at the end of use? There's been some investigations carried out in conjunction with private-public partnerships with universities looking into this, particularly in the case of EVs, because EV batteries, when you put them in the car, you only use them for about 20% of their expected life, and then they're no good basically for the automotive application. But that doesn't mean they're not good for other applications. So maybe you can upcycle them to a stationary storage system for a building or a microgrid. I know that some investigations at UC Berkeley have looked at that. But this continues to be a question that is investigated, and honestly, there aren't too many great answers right now for it.
Right, and then kind of follow up as far as lithium ion is concerned, those types of batteries, because of scarcity in the world. What do you think is really next? I mean, you touched on this a little bit as far as the future of storage.
Yeah, so the cobalt chemistries are particularly of concern on that particular topic. A lot of the rare earth cobalt comes from poor countries that are maybe being taken advantage of, and I don't like what's happening. Schneider, obviously we use tier 1 suppliers, and we have a huge push for sustainability and proper procurement of our supply chain and ethical supply chain and all that kind of stuff. But and other companies do too. But it's still a concern, and I think that's one driver that is pushing people towards an LFE chemistry. But it's not well thought out yet. It's not well solved yet either. We're kind of, the same thing could be said about solar modules. The manufacturing of them contains rare earth minerals. We don't have the best recycling for those yet either. So it's a continued concern. The industry, I think, is pushing towards a solid state battery that also uses a bit more common materials. So the industry is aware of these ethical concerns, supply chain concerns, and constantly striving to balance that with delivering a cost-effective product to the market that's going to also perform. And I think that we're in the early days of lithium-ion batteries and batteries in itself, and we're going to see tremendous innovation over the next 10 years in exactly these regards, on top of the performance technical aspects.
Yeah, you kind of touched on the last question was really about the social piece on the upstream and the supply chain regarding how are we extracting these rare earth minerals and getting them to market. Last is really a comment from a friend of ours who wanted to reference a publication that is called "Teaching the Duck to Fly." So if you can remember to Google that, and he said great point about purchasing lower cost energy to charge batteries or use solar during the day and letting the batteries get you through the rest of the day.
Yeah, absolutely. The duck curve is something that a lot of areas continue to struggle with. And I kind of like the approach California is taking, where they're changing the cost of their energy at different times of the day to drive different behaviors. So it's not necessarily just solved with technology. We can also do some behavior modification. Being a capitalist society, California is taking the approach to make it hurt in your wallet if you don't take those behavioral changes. And I think that's something we'll see expanded across the United States.
Yeah, I agree. Well, that does it for us. Bill, really appreciate your time, your expertise, and sharing with us. I learned a lot. I'm sure everybody else did, and we look forward to more conversations in the future. If anybody needs to get in touch with Bill, his information is here on the screen. He's very, very open about wanting to, share about these type of technologies and, of course, their products at Schneider. But again, Bill, thanks so much for joining us. This is perfect.
Yeah, thank you so much for the invitation. I really enjoyed the Energy Summit, and thanks again, Lee.
All right. So just want to remind everybody about our final summit that we have. I think actually you might need to stop sharing your screen.
Give me 1 second. There we go.
And so we have one more in the series this spring on March 18th. So try to join us. We'll be talking about embodied carbon in the built environment with Jane Lanier. So thanks everyone for joining us. Thanks for all your support, and we'll see you next time.